We live in a world built on ones and zeros. Every email, every video, every digital heartbeat is a vast tapestry woven from tiny definitive choices. A transistor is either on or off. A bit is either 0 or 1. It's a world of certainty. But what if the fundamental building blocks of computation weren't so certain? What if they could be both on and off, 0 and 1, all at once? This is the premise of quantum computing. It's not just a faster computer. It's an entirely different way of thinking about information itself. And the question is, how do we even begin to build such a thing? How do we harness the elusive, almost mystical rules of the quantum realm? First, we need to understand the qubit. Unlike a classical bit, which is a simple switch, a qubit exists in a state of superposition. Imagine a spinning coin. While it's in the air, it's neither heads nor tails. It's a probability of both. Only when it lands, when we measure it, does it choose a state. This quantum superposition allows a qubit to hold far more information. 2 qubits can represent 4 states simultaneously. 3 qubits, 8 states. The power grows exponentially, but this delicate quantum state is fragile. The slightest disturbance, a stray electromagnetic field, even a tiny vibration, and the superposition collapses. This is known as decoherence. It's the ultimate enemy of quantum computing. So, the first challenge in building a quantum computer is isolating these tiny, ethereal particles from the noisy universe. One of the most promising approaches uses superconducting qubits. These are tiny electrical circuits, often made of metals like niobium or aluminum. To keep them quantum, they must be cooled to incredibly low temperatures. We're talking colder than deep space, just a few thousandths of a degree above absolute zero. This requires specialized refrigeration units called dilution refrigerators. These are not your kitchen freezer. They use a mixture of helium-3 and helium-4 isotopes to create the coldest known continuous environment in the universe. The qubits are nestled at the very bottom of this elaborate structure, shielded from almost everything. Another approach uses trapped ions. Here, individual atoms, typically ytterbium or calcium, are stripped of an electron, making them electrically charged ions. These ions are then held in place by electromagnetic fields, like tiny individual pearls on a string of light. Lasers are used to cool them to near absolute zero and to manipulate their quantum states, encoding information. Each ion becomes a qubit. But the challenge isn't just creating a single qubit, it's connecting them. Quantum computers truly unlock their potential through entanglement. This is where 2 or more qubits become linked, such that the state of one instantly influences the other, no matter the distance between them. Einstein called it spooky action at a distance. To achieve entanglement, engineers use microwave pulses for superconducting qubits, or precisely aimed lasers for trapped ions. These interactions are carefully timed and tuned, like a conductor coaxing a symphony from the quantum choir. The control electronics are another marvel. They must send signals down to the qubits without disturbing their delicate states. Imagine sending a whisper across a Grand Canyon and needing it to arrive as a specific, precise instruction, all while maintaining extreme cold and shielding. This involves custom-designed microchips and intricate wiring. Often, these must also operate at cryogenic temperatures themselves. The sheer scale of the engineering is staggering. From the perfect vacuum chambers to the ultra-precise laser systems, each component is a masterpiece of scientific ingenuity. And the software? Programming a quantum computer isn't like writing code for your laptop. You're not just telling it what to do. You're orchestrating probabilities, designing quantum algorithms to exploit superposition and entanglement, Grover's algorithm for searching databases, Shor's algorithm for factoring large numbers, threatening modern encryption. These are not mere optimizations. They represent a paradigm shift in how we approach computation. The journey to build these machines is far from over. Today's quantum computers are still in their infancy, often with only a few dozen qubits, prone to errors from that ever-present decoherence. But the pursuit continues. Teams of physicists, engineers, and computer scientists are pushing the boundaries of what's possible. They are not just building machines. They are building bridges to a reality we can barely comprehend. A reality where a single particle can be in many places at once, where information is not just 0 or 1, but a shimmering spectrum of possibilities. When we look at the intricate dance of atoms inside a quantum computer, we are not just observing technology, we are glimpsing the fundamental strangeness of the universe itself. A ghost in the machine, perhaps. Or simply, a deeper truth. If this quiet exploration made you think a little differently, consider subscribing for more thoughts on the profound in the everyday.